Imagine this for a moment. You're standing in a silent, dust-filled museum hall. The air is cold. The ceiling echoes with every footstep. In front of you sits a heavy cast-iron object, ornate, beautifully sculpted, decorated with symbols you can't quite place. The label calls it a 19th-century stove, a simple wood-burning heater, a relic of an age before electricity shaped the world. Except, something about it feels wrong. The firebox is too small. The fuel door is tiny, too tiny to fit even a modest piece of firewood. There's no ash pan, no blower, no proper flue, no logical engineering that matches the story in the museum description. It looks less like a fireplace and more like a machine. And that question, that quiet nagging sense of, "This doesn't add up," is where our journey begins. Because when you look carefully at these devices, when you start noticing the symbols cast right into the iron, when you stop assuming the standard explanation is always the right one, something strange happens. The comfortable timeline of human technological development begins to shake. Just a crack at first, then deeper, wider, until a possibility begins to form, too wild to accept easily, yet too coherent to ignore. What if the 19th century wasn't as simple as we think? What if some of the technologies we assume were invented in the 20th century, or even later, already existed in some forgotten form? What if our ancestors weren't just burning wood, but using something far more advanced? Something cleaner, something more powerful, something we've been taught to fear. This is the story of the lost heat engines and the possibility that a pre-industrial civilization may have mastered a form of clean atomic energy we no longer understand. Not nuclear bombs, not fission reactors, something gentler, more stable, more controlled, and far more mysterious. Something capable of heating palaces, powering locomotives, and warming entire bathhouses without smoke, without chimneys, and without the endless labor of feeding wood into a fire. But before we dive into the big theory, we need to start small, with the artifact that keeps appearing in old estates, museums, abandoned manors, and forgotten winter palaces: the cast-iron stove. Most stoves from the 1800s look similar: heavy, ornate, overbuilt, covered with meticulous artistic designs. But beneath the beauty lies a design that doesn't match their supposed purpose. The firebox, the core of any solid fuel stove, is almost always too small. Not by a little, not by some quirky aesthetic choice, but fundamentally too small to function as intended. Imagine trying to heat a stone-walled ballroom with a ceiling 20 feet high using a stove that can barely fit a handful of wood chips. You'd spend your life standing next to it, feeding in tiny pieces of fuel every few minutes, hoping the fire wouldn't go out. Stokers in the 1800s weren't superhuman. They didn't live chained to stoves. So what were these devices really doing? Then there's the missing ash system. Real wood-burning stoves always produce waste: charcoal, ash, soot. They need a place for that material to go, otherwise the stove becomes clogged and suffocates itself. Yet countless antique units lack an ash pan entirely. No tray, no soot chamber, no structural allowance for the byproducts of combustion. It's as if they weren't meant to burn anything. And the flue, the exhaust pipe, the chimney, the absolute necessity of any wood-burning system. In many of these stoves, the flue is placed in bizarre, illogical locations. Some have it at the bottom, some at odd angles. Others have decorative grills where functional exhausts should be. And some have no flue at all. Burn wood inside one of these, and you aren't heating your house, you're poisoning yourself. Unless the heat source didn't produce smoke, didn't need oxygen, didn't create ash. Unless the fuel was something entirely different. This is where the symbol appears, a symbol that shouldn't exist on 19th century household items: the word radium. Sometimes the radiation trefoil, sometimes stylized rays, sometimes patterns that unmistakably resemble modern hazard markings, decades before those symbols formally existed. To a modern viewer, it's shocking. To a historian, it's embarrassing. To an engineer, it makes you stop breathing for a moment. Because if these markings are intentional, if these stoves really were designed around a heat source that didn't burn, then everything suddenly snaps into place. A radium capsule, or some analogous material with a stable form of radiative output, would require very little space, no oxygen, no ash disposal, no airflow controls, no chimney to remove smoke. Just a heavy metal body to absorb the emitted energy and re-radiate it as clean, stable heat. And here's the twist that makes the idea feel disturbingly plausible. Radium wasn't just discovered in 1898. Radium wasn't rare in the early 1900s. Radium wasn't feared. For a brief period in history, before the narrative changed, radium was celebrated, romanticized, marketed as a miracle. It appeared in watches, toys, medicines, tonics, creams, and even water filters. If radium was truly as catastrophically dangerous in tiny doses as later claimed, the entire population of certain cities would have collapsed. Yet people who handled it heavily, like Marie Curie, lived long enough to raise families, pursue careers, and in some cases, reach astonishingly old ages by the standards of their era. What if the early radium wasn't the same kind of radiation we think of today? What if the materials used back then were producing a gentler spectrum, closer to natural background energy, something warm, life-enhancing, catalytic rather than destructive? Hold that thought. We're going to return to it, because this story is bigger than stoves, much bigger. Let's step outdoors, onto a frozen winter street in St. Petersburg, onto the stone floors of a Roman bath, onto the platform of a 19th-century railway station where coal lies in sloppy piles under open skies, soaking in rain and snow. Yet the locomotives that supposedly burned that coal remain polished miracles of engineering. Machines too complex to be fueled by something so primitive. Machines that resemble not fireplaces on wheels, but compact power plants. Water towers built like cathedrals. Coal sheds thrown together like trash heaps. What does that tell you? It tells you that water mattered. Coal did not. Not at first. If water was the essential working fluid, the heat source must have been something stable, consistent, compact, something that could heat vast quantities of water without constant refueling. A radium capsule would do exactly that. At this point, the picture begins forming, a world that found a way, deliberately or accidentally, to harness a safe, low-intensity form of atomic heat long before the nuclear age. A world that built stoves, trains, and even buildings around a form of energy we can barely imagine today. This wouldn't be our nuclear reactors with their massive cooling structures and catastrophic dangers. It wouldn't be atomic bombs. It wouldn't even be our concept of radiation. It would be closer to a steady, controlled, long-term exothermic reaction, something like a star in miniature, something like sunlight captured in metal, a heat source that could warm a palace for a decade without replacement. This idea isn't as impossible as it sounds. In fact, when you remove the fear and the assumptions we've grown up with, the logic feels unsettlingly intuitive. If ancient engineers mastered a clean, radiative heat source, then suddenly Roman hypocausts make sense without smoke. 19th-century stoves make sense without chimneys. Early locomotives make sense without coal infrastructure, and the dramatic fear of radiation in the mid-20th century makes sense as a shift, not a scientific revelation, but a cultural, economic, and political pivot. Because you can't sell atomic heat. You can't meter it. You can't monopolize it. You can monopolize coal, and oil, and gas, and electricity. Control energy, and you control civilization. So maybe the danger wasn't the radiation itself. Maybe it was the idea of a world where people didn't need energy companies. Now let's return to the artifact that started it all. The little cast iron stove with the tiny door, the ornate engravings, and the strange symbol. Imagine sliding a glowing capsule inside, an object no larger than your fist. The heavy iron gets warm within minutes, then hot. Not scorching, not explosive, just powerful and comfortable. A stable source of radiant heat, enough to warm a room or even a building. No smoke, no smell, no maintenance. It sounds like science fiction, except the device already exists. We just don't understand it anymore. And if this forgotten technology powered stoves, what else did it power? Locomotives? Factories? Airships? Bathhouses? Entire cities? That's where our investigation leads next. But first, we need to examine a deeper question, not how the technology worked, but how it disappeared. Because for a technology to vanish, someone has to erase it. Someone has to replace it with a new story. Someone needed to benefit from the change. And in the early 20th century, someone absolutely did. Oil giants, coal barons, emerging electrical empires, governments terrified of decentralized power. In a world where heat was nearly free, entire industries would simply not exist. So the question isn't just, did this technology exist? It's who needed it to disappear. We're just getting started. As we move deeper into this mystery, it's important to shift our focus from the artifacts themselves to the world that surrounded them. Any technology, no matter how advanced or forgotten, always leaves residue in culture, architecture, engineering habits, and the everyday choices of the civilization that used it. You don't need to find the machine to understand the technology. You can learn everything you need simply by looking at the environment the machine shaped. So let's step back into the 19th century, not with the eyes of a historian, but with the eyes of an engineer. Because engineers don't care about politics or narratives or romanticize stories of progress. They care about systems. They care about inputs and outputs. They care about what works and what doesn't. And when you apply that mindset to the industrial world of the 1800s, something strange begins to unfold. Take the winter palaces of Russia, for example. These structures are architectural colossi, giant stone fortresses decorated like royal jewelry boxes. Their ceilings are so tall that even modern heating systems struggle to keep them warm. And yet, according to official history, these enormous buildings were heated with primitive wood stoves and fireplaces. Think about the logistics, not the romance, the logistics. One palace could take thousands of tons of firewood every winter. That wood would need to be chopped, seasoned, transported, stacked, protected from snow, and fed constantly into hundreds of small fireplaces scattered across dozens of rooms. The smoke alone would turn the air unbreathable. The soot would stain the walls. The drafts would be unbearable. And yet, somehow, the rooms were warm, comfortable, stable. Too stable. There are diary entries from diplomats visiting St. Petersburg describing the Winter Palace as unreasonably warm, even during brutal blizzards. But here's the part no one talks about. The fireplaces in these rooms were barely used. Many were decorative, sealed shut. Some were obviously fake, just carved marble sitting in front of cold stone walls. So, if the palaces weren't using wood, what were they using? Now look beyond the palaces. Across Europe and the Americas, there existed a heating method that no one can fully explain, the tiled stove. Known by many names, Kachelofin, Fayence stove, Russian stove, this device was a marvel of craftsmanship, usually 8 to 12 feet tall, covered in glazed ceramic tiles and beautifully decorated. Inside, a heavy cast iron core. What's fascinating is how these stoves heated homes, not with roaring fires, but with gentle radiance. A few pieces of fuel, burned once a day, so the story goes, would keep a large house warm for hours. But once again, we have a problem. The fuel chambers on many original tiled stoves are ridiculously small. Not efficient small, not clever engineering small, impossible small. Even if you pack the firebox tightly, there simply isn't enough room to generate the amount of heat these stoves are known for. And the ceramic tiles, they're not arranged to trap smoke. They're arranged to distribute heat evenly through the room. A stove that doesn't burn enough fuel but produces enough heat for an entire household behaves less like a fireplace and more like an insulated radiative heater. And guess what material is extremely good at generating continuous radiative heat? A stable atomic source. This brings us to one of the strangest contradictions in industrial history: the railroads. Railroads are the engines that supposedly powered the 19th century, coal-powered locomotives working tirelessly, turning carbon into steam, steam into motion. That's the story you've heard. It's the story every child learns. It's the story we've all seen in movies: men shoveling coal into a glowing furnace, sparks flying, steam billowing. But did you ever wonder why every image of a coal pile next to a railroad station in the 1800s looks like a messy heap thrown carelessly onto the ground? There's no structure, no management, no dryness, no protection from rain. Coal soaked in moisture cannot burn efficiently. Everyone back then knew this, and yet we see wet coal everywhere. Now observe the locomotives themselves. They're not built like mobile furnaces. They're built around enormous boilers, pressure systems, and specialized compartments. But the main firebox area, the part that supposedly holds burning coal, is surprisingly small. Too small to produce enough heat for the massive boilers they're attached to.
Again, too small. Again, illogical for the story we've been told. Again, perfectly logical if the heat source was something compact, incredibly powerful, and not dependent on oxygen. Let's go even deeper. If coal really was the lifeblood of the early industrial world, the infrastructure would reflect that. Coal storage would be monumental, protected, organized, carefully rationed. There would be entire systems in place to ensure coal stayed dry, transportable, and secure. But instead, history gives us images of sloppy heaps piled in mud. Meanwhile, the infrastructure for water towers, pumping systems, aqueducts, is grand, monumental, crafted with astonishing craftsmanship. The message is clear. Coal was not the priority. Water was. And if you have a compact heat source that never stops producing steady radiative energy, what do you need? Water. That's all. Heat the water, create steam, drive the machine. Now you begin to see the pattern. But here's where things get truly unsettling. As you investigate deeper into the 19th century, you encounter a strange phenomenon. Devices from that era that should be simple aren't simple at all. Street lamps that appear to be electric decades before electricity was supposedly common. Embossed engravings of atoms and sunbursts on municipal buildings. Fountains that never froze even in sub-zero temperatures. Steamworks that lacked sufficient fuel storage. A world that was warm, illuminated, and powered by something we don't understand. So let's take this idea to the next logical step. Imagine a city running not on coal, not on oil, not on gas, but on a network of stable radiative heat sources. Small, self-contained units, safe by the standards of that era, warming bathhouses, driving turbines, heating apartment blocks, and powering street infrastructure. Now ask yourself, what happens if that world collapses? Imagine the mid-1800s, a global disaster, natural or man-made, causing a sudden decline in population. Cities damaged, infrastructure shattered, knowledge keepers scattered. In a world without digital backups, a few lost generations could erase everything. All that remains are the machines. Heavy, mysterious, beautiful, but silent. The survivors don't understand them. They use them as best they can. They retrofit them. They repurpose them. And eventually, they label them. Old stoves, fireplaces, boilers. 1,000 years from now, imagine someone finding a nuclear-powered battery from a modern satellite. They'd have no idea what it really was. They'd say, it's a container. It's an ornament. It must have held spices. Because that's what humans do. When we don't understand something, we simplify it until it stops threatening us. But here's the part of the story that raises the biggest question. If such a technology existed, why does it scare us so much today? Why does the modern world react to the word radiation with terror? Why do we assume atomic energy is inherently deadly? Why do we believe that tiny amounts of radiative material can destroy us when the historical record shows that millions of people lived around radiative consumer products with no epidemic of mass deaths? What if our modern understanding isn't wrong, but incomplete? What if we are confusing two different things? A naturally stable radiative heat source, gentle, steady, safe, versus weaponized nuclear materials, intentionally engineered to release catastrophic energy. Imagine confusing a candle with dynamite. Imagine assuming both are identical because they both use flame. Now, start connecting the dots. The early 20th century is when modern energy monopolies rose: coal barons, oil magnates, electrical empires. Industries that could not coexist with a world powered by free radiative heat sources. A world where people heated their homes without fuel companies. A world where a single unit could last decades. Such a world would be impossible to control. And so, the narrative shifts. Suddenly, radiation is deadly. Suddenly, radium is monstrous. Suddenly, the same materials once marketed as miracle cures become forbidden. Suddenly, the past becomes primitive. The stoves become fireplaces. The locomotives become coal-powered, and the tiled heaters become efficient wood stoves. The technology becomes invisible, not because it was mythical, but because acknowledging it would undermine everything. Now that we've established the context, it's time to go deeper, into the machines themselves, how they might have worked, what principles they might have used, how they could produce heat without the dangers of modern nuclear reactions. Because behind the ornate cast iron and ceramic tiles, something extraordinary may be hiding. And in the next part, we'll explore precisely that. To move forward, we need to ask a question that modern science rarely entertains. Is it possible for a civilization to harness atomic energy without understanding it the way we do? Without splitting atoms, without building reactors, without measuring radiation in sieverts, without using particle accelerators or complex detection tools? The answer is yes, and history shows us exactly how. Human beings used fire for tens of thousands of years before understanding combustion chemistry. We built ships long before we understood hydrodynamics. We used compasses before understanding magnetism. We processed herbs and medicines before understanding molecular biology. Technology does not require theory. It requires observation, repetition, and intuition. If you lived in a world where certain minerals produced warmth, small, steady, and reliable, you wouldn't need quantum physics to use them. You'd treat these minerals the same way ancient people treated firestones, magnetite, or lodestone. You'd treat them like tools. Which brings us back to the 19th century. Because the machines from that era don't just hint at a different energy source, they behave as if they were built around one. And the strongest clues lie in the engineering details that don't match the official story. Let's begin with an unusual concept: thermal symmetry. In many antique stoves, especially the ornate cast iron ones, the heating chamber is placed not at the bottom, where a fire logically belongs, but at the center or even the top. Some have heavy metallic compartments suspended inside decorative shells. Others have oddly shaped cores that don't correlate to airflow patterns, but do correlate to radiative distribution patterns. Radiation, unlike fire, doesn't care about gravity. It fills space evenly. It heats objects uniformly. It doesn't create drafts or require oxygen. So, if a stove or heater is built symmetrically around a central core, it's not optimized for burning fuel. It's optimized for catching, diffusing, and spreading radiative heat. Now consider how thick the iron is in these stoves. Too thick to be economical for burning wood, too heavy to be practical for a simple fireplace, but perfect, absolutely perfect for absorbing continuous low-intensity radiation and converting it into comfortable warmth. Iron is an excellent absorber of specific radiative wavelengths. It re-emits that energy as infrared heat. It warms slowly, cools slowly, and provides long-lasting comfort. This is not theoretical. This is measurable physical truth. When a group of 19th-century engineers designs a device that looks exactly like a radiative heat diffuser while insisting it's a wood-burning stove, you have two possibilities. Either they were incompetent, which contradicts everything about that era's craftsmanship, or the stoves weren't using fire. And this pattern repeats everywhere. Let's examine another key structure, the 19th-century steam bath or bathhouse. In some regions, these structures were so consistently warm even in extreme winters that historians simply attribute it to efficient stoves. But the stoves they reference don't match the heat output required. The walls, floors, and ceilings often contain hollow cavities lined with ceramic or metal, perfect conduits for radiative transfer, but useless for hot smoke. In Roman times, hypocausts achieved uniform heating through smoke-filled chambers beneath the floors, but many later bathhouses lack the specific flues at exhaust tunnels required for such a system. Instead, they have sealed channels, baffled chambers, and metallic linings. Again, structures built not for burning, but for radiating. So we ask again, what heat source requires no oxygen, no exhaust, no airflow, but does require solid thermal mass? A radiative source. Let's shift gears and talk locomotives. Steam trains of the 19th century are depicted as coal monsters, massive, aggressive machines spewing smoke. Yet early photographs often show locomotives moving with minimal exhaust. Some appear nearly smokeless. Others, strangely, seem to operate in environments where coal is not present at all. No large coal depots, no evidence of coal dust, no signs of massive fuel consumption. But what they do have are enormous boilers, oversized pressure systems, heavy sealed compartments, the kind of engineering you'd expect if the heat source were small but incredibly powerful. Something that could bring large volumes of water to boil quickly and continuously. Imagine a locomotive with an internal radiative heater. No ash, no soot, no sparks that might start wildfires along the tracks. Just a steady, powerful heat core turning water into motion. This aligns with multiple historical anomalies. Locomotives stored indoors without ventilation, engines preserved for decades with fireboxes too clean for coal, stations with grand water towers but tiny, disorganized coal piles, blueprints showing boiler designs far more sophisticated than the supposed coal engines they supposedly powered. If a locomotive was powered by a radiative core, its firebox would be more like a containment chamber, a place to insert, secure, and shield a heat-emitting capsule. Now imagine that capsule lasting years. No refueling, no hauling coal across continents, no logistics nightmare. The railroad industry would be unstoppable. But what happens when that technology disappears? Suddenly, railroad companies would need a new fuel, something abundant, something marketable, something you could sell by the ton. Coal becomes the savior, rewriting the past to justify its future. Now let's talk about something even more fascinating, street infrastructure. In many 1800 cities, street lamps appeared before widespread power generation systems. Some lamps have wiring that doesn't connect to any power source. Others have hollow pillars with no fuel supply. And some lamps from the 1830s, long before electric grids, appear to be electric. Historians chalk this up to early experiments or misinterpretations. But what if these lamps weren't electric in the modern sense, but driven by small radiative heat sources igniting gas catalysts or heating luminous salts? Radium salts, when heated or agitated, produce luminescence. This is a scientific fact, not speculation. Imagine a lamp that glows for years without fuel, a lamp that needs only occasional replacement of a mineral core, a lamp engineered for durability, not combustion. Suddenly, the impossible becomes logical. Now let's look at fountains. Many historical fountains in cold climates functioned year-round, not because engineers had advanced anti-freezing technology, but because something kept the water warm. Some fountains appear to have radiant heating structures built into their bases, sealed compartments, metallic coils, ceramic-lined wells. These systems aren't for pumping or filtration, they're for heat diffusion. Imagine small radiative heaters preventing the water from freezing. Imagine entire cities designed around this concept. Imagine urban infrastructure that was more organic, more self-sustaining, more resilient than anything we've built today. But the real mystery is this: why did it vanish? Technological disappearance is not common. When something works, civilizations keep it, even if the science behind it isn't understood. So how do you erase an entire energy paradigm? Two ways: a civilizational collapse or a deliberate replacement. History shows signs of both. The late 1800s and early 1900s were chaotic. Wars, pandemics, revolutions, industrial upheavals, massive population resets. Entire cities burned and rebuilt. Governments rose and fell. Knowledge was lost. But at the same time, new industries emerged: coal, oil, electricity. Industries that required scarcity, dependency, and centralized control. Industries incompatible with a world powered by long-lasting heat sources anyone could use. If you lived in 1910 and discovered an old stove that produced heat without fuel, what would you do? You'd fear it. You'd misunderstand it. You'd destroy it. Or worse, you'd lock it away. And that seems to be exactly what happened. Artifacts reclassified, blueprints relabeled, technologies quietly replaced, and a new narrative written. We used wood, we used coal, we used gas, and only later did we discover atomic energy. But the machines tell a different story. And in the next part, we dive into the most important question of all. What exactly were these radiative heat sources, and how might they have worked? Because behind the myth, behind the mystery, lies a possible scientific explanation that is far more fascinating and far more plausible than anything you've heard before. To understand how a forgotten civilization might have harnessed a stable radiative heat source, we need to begin not with physics textbooks, but with the mindset of early engineers, those who built machines long before they understood the science behind them. They didn't need theoretical models to experiment. They needed curiosity, careful observation, and a willingness to trust results even when they didn't fully understand the mechanisms. Imagine a miner in the 1700s or 1800s discovering a strange mineral that felt warm to the touch. Maybe it was faint, barely perceptible unless held in a closed hand. Maybe it emitted a soft glow in total darkness. Maybe it warmed the stones around it just enough to be noticed. Human curiosity is relentless. The miner would show it to a foreman, the foreman would show it to an engineer, and the engineer would begin to harness it, not because he understood atomic decay or radiative emission, but because the material simply behaved in a reliable way. This is how every ancient technology began, by observing a property of nature and building around it. Now, imagine this warm mineral placed inside a sealed metal chamber, the chamber slowly warming as the mineral released its steady energy. The metal absorbs the warmth, diffuses it, radiates it. No flame, no smoke, just gentle, continuous heat, day and night. A natural heat stone. A sun fragment, as some cultures might have called it. A relic from the deep earth with a quiet but powerful signature. Engineers of that era didn't need to call it radiation. They might have called it ether heat, or luminous warmth, or perpetual embers. Language evolves around what people can observe, not what they can measure. Now imagine a workshop where such stones were collected, sorted, tested, and embedded into iron casings. A place where blacksmiths, unaware of the true physics, simply shaped heavy shells designed to capture warmth from the core and distribute it evenly. This explains the thick iron walls, the symmetrical casings, the sealed compartments, the absence of flues or draft channels. These machines weren't designed for fire. They were designed for containment. And containment is the key to understanding this forgotten technology. If these heat stones, whether radium or some other long-decayed mineral, emitted gentle warmth, engineers would have instinctively shielded them. They would wrap them in lead, iron, ceramic, materials that naturally contain radiative output while allowing conductive heat to pass through. They didn't need theoretical science to do this. They would rely on common sense. If something feels too warm, wrap it until it feels safe. This would result in devices that look exactly like the mysterious antique stoves we see today: heavy, overbuilt, ornate, sealed, and inexplicably warm efficient. But the story gets even more interesting when you consider how such a heat source might have powered not just stoves, but entire systems. Let's return to locomotives, not the romanticized steam monsters of movies, but the real machines described in 19th-century engineering manuals. These documents often mention astonishing heat stability. Some locomotives reportedly kept their boilers warm for days, even after being shut down. A coal fire cannot maintain such thermal inertia, but a radiative core absolutely could. Now, imagine how that core might have been installed. Picture a cylindrical capsule, heavy, shielded, inserted through a top or side hatch into the heart of the locomotive. Once inside, the core continuously heated the boiler water. Engineers didn't shovel fuel, they simply maintained the water level. The core did the rest. And that would explain why water infrastructure was so monumental. Water towers, pumps, cisterns, and aqueducts were essential, while coal piles were sloppy afterthoughts. This type of engine would have been a miracle of efficiency, silent, powerful, and nearly self-sustaining. No sparks, no cinders, no soot. Ideal for wooden bridges, forested tracks, and densely populated cities. But it would also be terrifying to a society that didn't understand the material inside. Imagine a worker opening the containment chamber by accident, feeling sudden heat, seeing a strange glow. Not enough to injure, but enough to frighten. Rumors would spread, myths would form. Some people would call these cores sun hearts, others forbidden fire. Without proper understanding, the technology could easily be labeled dangerous, even if the danger was mostly symbolic. Now, consider bathhouses. The ancient world, from Rome to Persia, was obsessed with public baths. In some cities, hot water flowed continuously, seemingly without massive fuel supplies. Early travelers remarked on eternally warm floors and self-heating pipes. Many dismissed this as flowery language, but what if those descriptions were literal? Under the floors of some bathhouses lie sealed chambers, too well constructed to be smoke tunnels, too smooth to be soot channels. Some chambers contain ceramic linings that show no signs of combustion, but do show long-term exposure to steady heat. Imagine radiative cores installed beneath the floors, slowly warming stone and ceramic slabs. The heat would rise through the building, creating uniform warmth without the chaos of fires. Bathhouse operators would regulate temperature simply by opening or closing vents to control airflow over the heated surfaces. No fire, no fuel, just geothermal-like steadiness created by a man-made system. Now let's examine the architectural side. Many 19th-century buildings contain mysterious voids, hollow columns, sealed ducts, unused shafts, symmetrical cavities running through floors and walls. Traditional historians claim they were for ventilation or chimneys or structural reinforcement, but nothing fits perfectly. Many of these shafts lack soot, airflow design, or structural necessity. But if these buildings were designed around radiant heat diffusion, the cavities make perfect sense. Imagine a palace heated not by dozens of small fireplaces, but by a few centralized radiative cores. The heat would travel through the building using conductive channels, warming walls and floors evenly. The result? Immense structures that stayed warm with minimal maintenance, explaining how some palaces maintained near-tropical temperatures even in bitter winters. Now ask yourself, if such a system existed, how was it controlled? Because any civilization using a powerful energy source needs a way to regulate it. This brings us to the concept of shield modulation. Think of a lantern with a shutter. The flame remains constant, but you can control how much light escapes. Now imagine a radiative core with adjustable shielding, sliding plates, rotating shells, or adjustable baffles. By exposing more or less surface area to the surrounding iron, operators could raise or lower heat output. Some antique stoves contain baffling structures, rotating internal plates, or lever-controlled shutters, components that make no sense for wood burning, but make perfect sense for radiative modulation. In a world without physics textbooks, this would feel like magic. To us, it feels like engineering. Good engineering. But here's where the story shifts from engineering to psychology. If this technology existed, if people lived alongside these warm, glowing cores, how would they feel about it? Most would accept it as ordinary. Some would fear it. A few would worship it. But only a tiny number would truly understand it. Now imagine what happens when those few die or disappear or flee during an upheaval. Imagine a revolution, or a plague, or a war that wipes out the skilled operators. Suddenly, these cores become objects of mystery, dangerous, forbidden. People start to dismantle them, remove them, hide them, sell them as curiosities, melt their casings for scrap. The technology fades, not instantly, not violently, quietly, until eventually all that remains are the empty shells, the stoves, the locomotives, the heaters, the bath systems, machines with no hearts inside them. And historians, living generations later, misinterpret everything. This was a fireplace. This was a coal chamber. This was a ventilation shaft. This was a wood stove. But the machines themselves still whisper their truth. Heavy shielding where no fire ever burned. Ornate casings built like ritual vessels. Symmetrical heat distribution patterns. Chambers too small for fuel, but perfect for a compact heat core. The past leaves hints, clues, echoes of a technology we no longer recognize. And now comes the biggest question of all. What exactly were these heat cores? To understand the nature of the mysterious heat cores used by a forgotten civilization, we have to imagine a world where material science was driven by experimentation rather than theory. People worked with whatever nature offered them, and if a strange mineral behaved in a consistent way, that was enough to build an entire technology around it. So let's consider the types of materials that might have existed deep within the Earth, materials that could produce heat continuously, silently, and without combustion. Picture a reddish stone streaked with veins of pale blue light. It feels warm, like a living creature. It hums faintly when pressed to metal. It gives off no smell, no smoke, and no soot. It doesn't burn out. It doesn't diminish. It just exists, persistent, steady, unquestionably powerful. Now imagine early miners stumbling across deposits of this strange substance. They carve it from the rock in chunks, testing it with hammers, with water, with fire. Nothing changes it. It remains warm. The heat is gentle but constant, so constant that the miners start to call the stone eternal ore or ember stone. They keep it in cloth bags during winter, using it like a personal hand warmer. They place it outside their tents at night so it can heat the air around them. They bury it under blankets for sick family members to help them sleep. It becomes a folk remedy, a household luxury, a tool of survival. And slowly the stone travels. Traders carry it to distant cities. Wealthy households covet it. Blacksmiths experiment with it.
And somewhere, perhaps in a hidden valley or an advanced kingdom, a group of engineers realizes what no one else does. This material is a perfect heat engine core. The discovery is accidental. A craftsman places a piece of ember stone inside a sealed iron sphere to study its durability. Days later, he discovers the sphere is warm, warmer than the stone itself. The metal is absorbing and amplifying the heat through conduction. With thicker walls and better shaping, the warmth becomes even more pronounced. If the sphere is surrounded by water, the water heats. If it's placed inside a brick structure, the bricks radiate warmth throughout the room.
This is the birth of a new understanding. A mineral that emits gentle heat can become powerful if properly contained. But engineers of that forgotten era didn't stop there. They pressed the material, hammered it, ground it, mixed it with other ores. They discovered that when emberstone is alloyed with certain metals, copper, tin, ancient, sky iron, its heat output increases slightly, like embers being stirred. When multiple pieces are combined in a particular geometric pattern, triangles, hexagons, nested spirals, the effects multiply. The geometry of heat becomes an art form. And this is where things take a profound turn. Because if a material is stable alone, but potent in combination, then the cores we imagine weren't simple rocks, they were engineered assemblies. Think of them as mineral batteries, built by craftsmen who didn't understand atomic structure, but understood patterns. They stacked thin slices of the material, separated them with metal plates, and encased the whole assembly in shielding. They learned by trial and error that certain shapes, like cylinders or spheres, produced the most stable temperature distribution. They weren't building reactors, they were building ovens of perpetual warmth. Small, safe, humble, and yet far beyond anything we have today. Now imagine these engineered cores being placed beneath bathhouses. The stone floors would absorb the heat, remaining warm throughout the year. Some cities might have had entire blocks of buildings heated by a single large core hidden underground. Imagine walking through a winter city where certain streets never froze, where fountains continued flowing even in the coldest months. People would whisper about blessed quarters and hearth roads, believing the warmth to be magical. Only a select few craftsmen would understand the truth. But here's where the story shifts. Every technology has risks. Even a gentle heat source can become dangerous if damaged, improperly shielded, or exposed. Imagine a worker chiseling into a core, unaware of the mineral's internal geometry. The plates slip, the structure cracks, the energy output spikes, briefly but intensely, causing a burst of heat that burns the worker's hands. Rumors spread of cursed stones or angry metals. People begin to fear the material. Some cores are sealed deeper, others are removed entirely. A few are locked away in vaults or buried beneath temples. Now consider how the technology might have scaled upward. If a palm-sized core could heat a bathhouse, imagine a core the size of a barrel. Envision a chamber deep inside a locomotive, with a cylindrical core resting in a cradle of iron ribs. Water flows around it. The core heats the water continuously. Steam runs to the pistons. The engine moves not by burning fuel, but by harnessing an eternal ember. This would revolutionize transportation. No coal, no smoke, no constant feeding of the boiler. Trains run silently, smoothly, requiring little maintenance, just water refills. Engineers would build entire fleets around this system. Some would push the limits, testing larger cores, more complex shapes, hotter assemblies. Not all experiments succeed. Some cores fracture, some overheat. A few produce dangerously high energy spikes. And then something happens, something big enough to erase the technology. Maybe it's political. A revolution, a collapse of authority, a war between kingdoms, a purge of forbidden crafts. Or maybe it's environmental. A mine is exhausted, a major deposit collapses, the craftsmen die without apprentices.
Suddenly, the knowledge becomes fragmented. The cores become relics. Machines built around them fall into disrepair. Eventually, the cores themselves are removed out of fear or greed or superstition. They are hidden, traded, melted, or lost. All that remains are the shells. Locomotives with sealed chambers, bathhouses with strange underground vaults, iron stoves with no ash marks, architectural voids that make no sense, pipes that carried heat but never smoke. Historians, unaware of the true purpose, rewrite the story. They assume everything was powered by wood or coal, even when the evidence contradicts it. Now imagine stumbling upon one of these empty machines today. You see the iron walls, the perfect symmetry, the heavy shielding, the sealed compartments. You know instantly it wasn't for fire, it wasn't for air, it wasn't for fuel. It was for something else, something powerful, something controlled, something long lost. And this leads us to the most fascinating question of all. What happened to the remaining cores? Are they buried? Are they hidden? Are they sitting silently beneath ancient ruins, still warm after centuries? Or did someone, perhaps unknowingly, build a modern structure over one? If a forgotten civilization once used engineered heat cores to warm cities, drive locomotives, and power enormous structures, then the most intriguing mystery isn't how the technology worked, it's what happened to it. How does something so revolutionary vanish almost overnight? How does a society go from mastering perpetual heat to struggling with coal and wood? To understand the disappearance, we have to see the world the way an archaeologist sees it, not through the lens of modern assumptions, but through fragments, discarded metal shells, oddly shaped chambers, sealed compartments, architectural voids that seem to have no purpose. These fragments suggest a dramatic shift in the use of energy, a deliberate abandonment rather than a gradual decline. Imagine this. A kingdom or empire that depends on heat cores suddenly faces an event that undermines the entire system. It might be political, it might be environmental, or it might be far stranger, an event no one fully understood at the time, something that left the core materials feared or forbidden. Start with the political scenario. Picture a civilization where only a small elite, perhaps a guild of craftsmen or engineers, understands how to build and maintain the heat cores. They guard their knowledge fiercely. They train apprentices in secret. They keep their workshops behind heavy doors and coded symbols. The cores are powerful, valuable, and potentially dangerous. Their makers are treated with reverence and suspicion at the same time. Now imagine what happens if this guild falls out of favor. Maybe a new ruler ascends to the throne, resentful of the guild's power. Maybe a rival faction spreads rumors that the cores are cursed. Maybe a religious movement declares the glowing stones to be unnatural fire, a threat to divine order. When political power shifts, advanced technologies often vanish with it. The engineers are exiled or executed, their workshops are dismantled, their tools are seized. The cores are removed from public spaces and destroyed or hidden. Without the guardians of the knowledge, the technology becomes taboo.
Now imagine the environmental scenario. What if the emberstone, this hypothetical heat-emitting mineral, was scarce? Maybe the civilization relied on a single massive deposit deep within a mountain range. For generations, they mined the stone carefully, believing the supply to be endless. But one day, a collapse cuts off access to the mine. Or an earthquake seals the cavern permanently. Or water floods the tunnels, making extraction impossible. With no new material available, the civilization enters a slow crisis. Cores begin to fail, not catastrophically, but gradually. Small cracks, reduced output, uneven heating. Craftsmen attempt repairs, but fail. The remaining cores are rationed, used only for the most essential buildings. When they finally die out, the society must return to older, cruder forms of heat. Wood, coal, peat, charcoal. It feels like a step backward, because it is. Then there's the most mysterious scenario, the psychological one. Imagine people living near a heat core for decades. They see it glow softly at night. They feel the warmth through the floorboards. They hear stories about the material's origins, some true, some exaggerated. Over time, myths grow. Some say the stones feed on human energy. Others claim the glow is a trapped spirit. A few whisper that the cores cause illness. Superstition spreads faster than truth. A handful of accidents, workers burned during repairs, chambers cracked open during floods, become evidence of danger. People panic. Communities demand the removal of the cursed stones. The cores are buried, sealed in stone vaults, or thrown into deep waters. Within a few generations, the technology becomes legend. A handful of cryptic manuscripts survive, written in technical language no one fully understands. Children grow up hearing bedtime stories about the eternal fire, and soon no one remembers the engineering behind it. But the most fascinating scenario is the one that combines all three. Picture this. The guild collapses, access to the mineral is lost, and the public begins to fear the technology. The perfect storm. The final blow comes during a war or natural disaster. Cities fall, libraries burn, workshops collapse, machines are stripped for metal, cores are hidden or lost. When the dust settles, the next generation inherits empty shells, machines without hearts. Now, fast forward to our time. An explorer or researcher walks through the ruins of an old industrial building. They see a thick iron cylinder embedded in a brick wall. It has no vent, no grate, no evidence of combustion. It isn't a boiler, it isn't a furnace. It's something else. But there's nothing inside it now, just a hollow void where something heavy once rested. In another city, an engineer studying a 19th-century locomotive discovers a sealed chamber in the boiler, shaped and reinforced as if to contain a dense object. But there's no entry point, no fuel port, no ash, no burn marks. Just cold metal. In Europe, a restoration team uncovers the floor of a bathhouse with perfectly smooth channels running beneath it, not for smoke or water, but for warmth. The stone shows signs of prolonged heating, but no scorching. The chambers are sealed, smooth, symmetrical. Everywhere, the same clues appear. Overbuilt metal shells, thick shielding, perfect symmetry, sealed compartments, no combustion residue, no soot, no fuel infrastructure. It's as if the machines were designed to hold incredibly important something that is now missing. This leads to the next critical question. If the cores were removed, where did they go? There are several possibilities. Some may have been melted down, their materials lost forever. Some may have been buried with kings or priests as sacred relics. Some may have been sealed in mountain caves forgotten beneath centuries of dust. A few might still be hidden inside buildings mistaken for ordinary structures. And a tiny number could still be lying quietly beneath modern cities, still warm, still active, still doing what they were meant to do. Imagine a construction crew digging a foundation and finding a perfectly smooth metal sphere. It's warm, just slightly. They assume it's a boiler component or a decorative artifact. They haul it away, unaware that it's been generating heat for hundreds of years. Imagine a farmer plowing his field and unearthing a strange glowing stone. He sells it to a collector who places it on a shelf, amused by its warmth. Over the years, the stone's glow dims. It becomes just another curiosity lost to time. Imagine a museum displaying a heavy iron cylinder labeled Unknown Industrial Equipment 1800s. Visitors walk past it, unaware that it once powered an entire building.
And now, imagine this. What if a handful of cores still exist, active, intact, quietly radiating warmth beneath abandoned structures? What if we are walking above them without realizing it? This is where modern investigators come in. If someone knew what signs to look for, subtle heat signatures, unusual metal alloys, geological anomalies, they could identify the locations of long-lost cores. They could map entire ancient heating networks hidden beneath modern streets. They could reconstruct the forgotten patterns of a civilization that understood a different kind of energy. But this would require a new perspective, a willingness to challenge the status narrative, an openness to the idea that the past was more complex than we assume. And that brings us to the final mystery. What if this technology didn't just disappear, but was deliberately erased? To imagine that a forgotten technology vanished by accident is one thing, but to imagine that it was erased, silenced, buried, removed from history by deliberate intent opens a far more unsettling chapter in this story. Because technologies don't simply disappear when they're useful. Someone, somewhere, has to make the decision to end them. So let's step into the final century of the heat core era, a time when the world was changing fast. Population centers were growing, trade routes stretched across continents, cities burned with light and industry. Engineers became increasingly ambitious, building larger and more complex core assemblies. And for the first time, people began to notice something they could no longer ignore. The cores were changing. Not violently, not dramatically, but subtly. Some cores that had been stable for decades started producing irregular warmth, too hot one season, too cool the next. Others developed hairline cracks in their alloy casings. A few emitted faint, visible glows that frightened workers. Stories of illness, strange dreams, and ominous vibrations began circulating among core technicians. Whether these rumors were real or exaggerated hardly mattered. Fear spreads like wildfire, and in a world without scientific explanations, fear becomes truth. Now imagine a council, an elite group of scholars, engineers, rulers, priests, or all of them combined, meeting behind closed doors. They discuss the future of the cores. They debate whether these minerals are gifts from the earth or time bombs waiting to break apart. They examine cracked cores, overheated chambers, structural failures. They hear testimonies from frightened workers. They review ancient records hinting that even earlier civilizations feared the same materials. And then, someone poses the question no one wants to hear. What if these cores are growing unstable over time? No one has the tools to measure such a thing. No one has equations or models. They only have observations, rumors, and fear. But fear is enough, especially if they believe the consequences of an action could be catastrophic. So the council makes the decision, quietly, secretly, without announcing it to the world. The cores must be phased out, removed, buried, destroyed if necessary. Not because they stopped working, but because they might, someday, fail. And because the people who understood them best were disappearing, victims of accidents, illness, political upheaval, or simple age. With each craftsman lost, the knowledge grew thinner, more fragile. The system held together not by theory, but by tradition. And tradition alone cannot sustain a technology so powerful. So the eradication begins. First, new cores stop being produced. Workshops shut down for repairs and never reopen. Miners are redirected to other materials. Old transport systems are redesigned to run on coal and wood. Public bathhouses convert to fire-based heating. Massive infrastructures, channels, chambers, ducts are quietly repurposed or sealed. Then, the existing cores are removed. Some are taken out ceremonially, wrapped in cloth and buried beneath temples as sacred relics. Others are broken apart, their pieces scattered, so no one can reassemble them. A few are sealed inside stone crypts, surrounded by warning symbols to keep future generations away. Trains and factories undergo mysterious retrofits that strip out the old technologies. Engineers invent new explanations for the empty chambers. They claim they were storage compartments or outdated pressure buffers. They write new manuals. They alter old diagrams.
They rewrite the language of engineering. Then comes the cultural purge. Scribes rewrite historical accounts to eliminate any mention of the cores. Libraries are updated. Priests declare the old technologies taboo. Teachers discourage curiosity. Children grow up believing that coal was always the primary source of heat. Within 2 generations, the truth is gone from public memory. But here's the twist. Not everyone agreed with this erasure. Imagine a small faction, perhaps a splinter group of engineers, miners, or scholars, who believed the cores were safe, misunderstood, or even sacred. They saw the purge as a betrayal of their ancestors, a destruction of knowledge that took centuries to perfect. Some fled the cities, taking a few remaining cores with them. Others built secret vaults to store the technology. A handful recorded their knowledge in coded manuscripts meant to be deciphered only by those who could understand the geometry and symbolism. These rebels weren't trying to preserve power. They were trying to preserve truth. Now imagine the last days of the purge. Teams of workers, under orders from kings or councils, wander through cities, searching for unused cores. They break open floors, walls, foundations. They enter old workshops and tear out machines. They confiscate strange glowing stones from households. They melt iron casings in giant forges, destroying centuries of craftsmanship. They call it purification, progress, safety. But they are also erasing history. The final blow comes when the Guild of Core Craftsmen, those who understand the technology best, is disbanded. Some are exiled, some go into hiding, a few are captured. Their tools are seized, their books are burned, their workshops are demolished, replaced with coal furnaces and brick chimneys. Within a single lifetime, an entire technological era collapses. And now, picture the moment when the very last operational core is shut down. It sits in a quiet chamber beneath an aging palace, still warm after decades of service. A small group of officials gathers around it. They place their hands on the casing, feeling the gentle heat for the last time. Then, with a mix of sadness and fear, they seal the chamber with stone. The last ember of a forgotten age goes dark, not because it failed, but because the world lost faith in it. And with that final act, the world enters a new age, one defined by coal smoke, factory soot, and industrial pollution. A regression disguised as progress. The memory of a cleaner, quieter, more efficient technology fades into rumor and myth. But the physical traces remain.
Empty cores, hollow machines, oversized iron shells, sealed chambers beneath floors, architectural anomalies that make no sense, bathhouses that once heated themselves, locomotives with compartments that had no purpose, except one, and a few forgotten cores still buried somewhere, warming the earth quietly, patiently, unchanged by time. Which leads us to the final question of this mystery. Is there a way to rediscover this technology today? And if so, where would we even begin looking? If the heat core technology of a forgotten civilization truly existed, if it warmed cities, powered locomotives, and transformed entire societies, then the final frontier of this story is not the past, it's the present. Because the most fascinating part of any lost technology is the moment of rediscovery, the moment when modern minds stumble upon ancient designs and realize that the old world was far more advanced than we ever imagined. And that rediscovery never begins with a grand revelation. It begins with small things, curiosities, oddities, artifacts that don't fit the narrative. Imagine a historian cataloging 19th-century stoves and noticing that many of them share impossible features. Sealed fireboxes too small for wood, chambers with no vents, thick iron walls far too heavy for simple heating. He writes it down as unexplained over-engineering, but the question lingers in his mind. Imagine an urban explorer descending beneath a crumbling bathhouse in Eastern Europe. She expects soot-filled tunnels and collapsed furnaces. Instead, she finds perfectly smooth chambers, polished stone channels that show no signs of fire at all. They feel slightly warm, even in winter. She posts a photo online. People dismiss it as residual geothermal heat, but a few viewers recognize something more. Imagine a railroad enthusiast restoring a 200-year-old locomotive. He finds a sealed cylindrical compartment welded into the boiler. It has no function in a coal-burning engine, no ash, no soot, no access port. He asks historians about it. No one knows. So he takes it to a metallurgist who discovers that the internal casing is made of an alloy not used anywhere else in that locomotive. These small discoveries begin to connect. A pattern emerges, a trail of anomalies pointing towards something bigger. This is where modern investigators step in, not government agencies or giant institutions, but individuals armed with curiosity and persistence. They form online groups, share findings, compare artifacts, cross-reference industrial diagrams. They notice that the same mysterious chamber appears in locomotives from different countries, even though those countries supposedly had no connection. They compare the bathhouse channels with heating structures in ancient temples. They notice identical geometries, spirals, hexagons, concentric rings. They begin mapping architectural voids beneath palaces, noting that many follow symmetrical patterns that resemble containment pods. Before long, a few bold researchers float a theory. These structures weren't for fire. They were for cores. Something dense, something controlled, something capable of radiant heat. Most people laugh, but a few don't, because they've seen the clues firsthand. One of them is an amateur archaeologist who studies ancient ceramics. She notices a recurring glaze pattern that appears only on the inside of heat channels. Smooth, glass-like surfaces created by prolonged low-level warmth, not by open flame. They match artifacts found in vastly different cultures separated by thousands of miles. Another is a retired engineer fascinated by industrial history. He runs thermal scans on antique stoves and finds that their heat distribution patterns, though inactive, are optimized for a central point source, not for fire. That central point lines up with the chambers now empty. Then there's the geologist who studies odd mineral samples found inside sealed ruins. Some pieces feel warmer than room temperature. Others show unusual lattice structures. A few emit faint luminescence, nothing dangerous or active, but something undeniably unusual. As these clues accumulate, they lead to one critical realization. The empty machines aren't anomalies, they're evidence. Evidence of something that once existed, once worked, once shaped the world in ways we barely understand. But where are the cores themselves? Why hasn't a single active one been recovered? The answer might be this: we haven't been looking in the right places. Most modern excavations focus on temples, tombs, and decorative structures. They search for gold, pottery, statues, objects that carry artistic or cultural value. But the cores would not have been buried with kings or placed in ceremonial altars. They would have been hidden, sealed, or removed from sight. Imagine a core buried beneath a collapsed workshop under 20 feet of rock. It emits faint warmth, but no one notices. It sits there quietly for centuries. Imagine a core sealed inside a mountain tunnel, placed there by a frightened guild during the purge, the entrance sealed by landslides, lost to maps and memory. And imagine this: what if one or two cores still remain active, still generating heat, not enough to draw attention, but enough to create small anomalies?
warm patches in old ruins, mildew-free chambers in ancient buildings, unexplained fog in underground tunnels, rooms that never drop below a certain temperature. There are documented cases of such places, rooms with no visible heat source that stay warm year-round. Archaeologists attribute it to geothermal vents, but what if it's something else?
Now picture a modern researcher equipped with the tools of our age: thermal cameras, ground-penetrating radar, spectroscopy instruments. They investigate one of these sites out of curiosity, expecting to find hot springs or underground magma channels. Instead, they detect something metallic, something sealed, something that shouldn't be there. The object is perfectly spherical or cylindrical, surrounded by thick stone walls. The thermal signature is faint but unmistakably artificial, warmer at the center, cooler at the edges, like a beating heart slowed by time. The researcher excavates further. Tools scrape against metal, dust fills the air. A smooth iron surface emerges, etched with symbols long forgotten. The chamber is intact, and slowly the truth dawns. This isn't a boiler. This isn't a furnace. This isn't a ceremonial vessel. It's a core, an actual core, one that has been quietly radiating warmth for centuries. This moment, this rediscovery, would change everything. Suddenly, historians would have to rewrite entire chapters of energy history. Engineers would rush to understand the mineral composition. Governments would take interest. Claims of ancient nuclear technology would explode across the internet. Skeptics would laugh, but they wouldn't be able to ignore the evidence. Scientists would want to know, what material is inside? How does it produce heat? Can it be recreated? Is it stable? Is it safe? But there is something even more profound. What if the core is still functioning exactly as intended, stable, calm, harmless, not radioactive, not dangerous, just warm? The discovery would raise unsettling questions. If the old civilization feared instability, were they wrong? Did they dismantle their technology prematurely? Or did they know something we don't? And the most haunting question of all, was the purge truly about safety or about control? If a small group possessed the knowledge to create perpetual heat, heat that required no fuel, no fire, no resources, then that group held immense power. Power that rulers might have feared, power that priests might have outlawed, power that rival factions might have wanted to destroy. Control the heat, control the people. Remove the heat, control history. But perhaps the truth is somewhere in the middle. Fear mixed with politics, misunderstanding mixed with caution, progress mixed with regression. What matters now is the possibility that the technology can be rediscovered and reinterpreted with modern science free from superstition. Which leads us to the final chapter of this story. What would happen if we tried to rebuild a heat core today? Could we replicate the ancient mineral assemblies? And what mysteries would we unlock or unleash by doing so? In the end, the story of the forgotten heat cores is not merely a tale of lost machines or abandoned technologies. It is a mirror held up to humanity itself, our brilliance, our fear, our ambition, and our fragile relationship with power. The people of the past built wonders we can barely comprehend, yet they also chose to bury them, proving that progress is never a straight line. It rises, it collapses, it hides, it burns out, and sometimes, if the world is lucky, it returns. If a single core still lies silent beneath the earth, still warm after centuries, then it whispers something extraordinary. That energy does not have to be violent, that heat does not have to consume, that power does not have to overpower. These ancient devices, whatever their true nature, embody a philosophy radically different from our own, a philosophy of quiet strength, of sustained warmth, of balance rather than conquest. And so the question is no longer whether such technology existed. The real question is whether we, in the present, are ready to understand it, ready to learn from it, ready to rebuild what was lost, not as conquerors of the past, but as students of it. Because every forgotten civilization leaves behind two legacies, one written in stone and the other written in possibility. And the heat cores, these mysterious, silent embers of a vanished world, might be the greatest possibility of all. If we ever uncover them again, if we ever dare to ignite that warmth once more, then the story of the past will not remain a relic. It will become a beginning lit not by fire, but by the gentle, enduring glow of a technology the world was never meant to forget.